Hi. So today's episode, we're going to talk about the functions and continuous functions and a so-called Weierstrass theorem. Okay. So before we talk about that, so let's first define the functions. Okay. So normally we just use those functions, but we have never defined those things, right? Okay. So for simplicity, we say that given some sets, okay, x and y. Okay, we call a function f. Okay, so this is just some map, okay, and written as this f from set x to y, okay, as a function from x to y. So this is a function if we have some element in x, then we have this operator f, this map f taking x, and that has to be inside of this y. Okay. Okay, but we didn't define this sort of this map or this operator, right? So that'll be something further, but we're not going to do that for this episode, but we could talk about that later. Okay, so and for example, we can have some set x, okay, and some, let's say, some set y. Okay, so if we have some point x inside of x, and we can map this to some point fx that is in y. Okay, so we can call this this as a function. Okay, good. So that is just some sort of mapping, right? So we just relates those 2 points in the two sets. Okay, that is so-called a function. Okay, so and next we can give a name, okay, of some sort of, we know the domain of a function, and then we're going to have some image. Okay, so let's say for some subset of x, an image of this s is this fs. Okay, so we can either write fx, those elements, or we can write some subset of that. Okay, fs, and that will be some element in y. If we have some element in x, and we can map this x to this y. Okay, so again, in this little picture, we could, for example, let's say we have this to be our s, okay, and we can map this to something like this. Okay, so this would be our fs as our image. Okay, good. So this is pretty straightforward, and we're gonna have some pretty special functions. Okay, we call a surjection is as follows, or it's also called onto, okay, mapped onto something. So f is a surjection if, let's say, for any y there exists some x such that this y is mapped from x. Okay, so in other words, we can map all of those x to the set y. Okay. So we don't leave anything left, right? So we don't leave anything behind. So we can map everything from x to y. Okay. For all the y, we can map some x to this, right? But we didn't say that we map all of those x, but we just map all of those y. Okay. Good. And okay, and we have defined the image. We can also define some inverse image. Okay. So let's say for some set t, okay, inside of y. So an inverse image of this t, okay, that would be f inverse of this t. That would be some x, and there exists some y such that y equals fx. Okay, so we simply call this as the inverse image of t. Okay, if we have the map from x to y, and this y is inside of this t. Okay, and then we call the set of all of those x's to be the image of this t. Okay, so that would be a definition of an inverse image. Okay, and we can also define some, besides the surjection, we can also define an injection. So we call the function f, so this is also called 1-to-1 map. F is an injection is if f for x1, x2, they are not the same. We can always have x1 and fx2, they are not the same. Whenever x1 not equals x2. Okay. And we can even have something. So this injection is saying that so if whenever we have some two different things in x, two different points, then we're gonna have those two value of functions, they're not the same. Okay, so this is called an injection. So that is a map from 1 to 1. Okay, so if some function is both injection and surjection, and we're gonna call that as a bijection. Okay, so f is a bijection if f is a surjection and an injection. Okay. Okay. Good. So those are some definitions for functions. Okay, so next we're going to talk about the continuous function. Okay. Okay, sometimes we can define the continuity by the limits, right? But here we're going to define this in some alternative ways. So let's consider a function from Rn to Rm. Okay, so we say this f is continuous if for all x in Rn, okay, and for all some epsilon, small number epsilon, there exists some delta, positive number delta, such that for all x prime, some other point inside of the delta ball centered with x, such that this fx prime is also inside of this epsilon ball of fx. Okay, so this is saying that if we have some, so for all the x, okay, and for all those points x, and for all of those any distance, any epsilon balls, okay, and there's gonna be some delta, some small positive number delta, such that for some other point, okay, pretty close to this x inside of this delta ball, we're gonna have this function value taking x prime to be inside of the epsilon ball of fx. Okay, so that's also pretty straightforward. Right? So if that is simply saying that if we have some value that's pretty close to our x, then in the fx fx prime, that has to be pretty close to our fx. Okay, and for example, we're gonna have this picture. So this would be in R1. Okay, also fx is in R1. So both are real values. So let's say we have some random functions. Okay, and here this would be our x. Okay, let's say this is our x prime. Okay, so we have this some delta ball. Okay, so this is inside of, let's see, this is delta. Okay, those are deltas, and this x prime is inside of this delta ball of x. Okay, and for all of those epsilon, so this fx prime, that has to be inside of some epsilon ball of fx. Okay, so this has to be inside of some epsilon ball. Okay, so that'll be also, we can use this as a ball or just some intervals on this axis. Okay, all right, so we can always find this point that is pretty close to that point, right, for any epsilon ball or any radius of that ball, right? Okay, so this is a good example. Okay, for a bad example, for a counterexample, let's say if we have this x and fx here. Okay, what if we up to here we have this value that is not included on this part, but we're gonna continue on here. Okay, and so on and so forth. So from here we can see that if we're gonna set this value of to be x, okay, and let's say we put this x prime to be here. Okay, let's say we put this x prime on the left, right? So there will be a problem, right? So that means for any so let's say this is included in delta ball, okay, but maybe this is inside of some big epsilon ball, okay, but we have to make sure for all of those epsilon, right, for all epsilon. So for this epsilon, then this is not, then this would be too far, right? So this is not good. So this violates the continuity. Okay. So this is not continuous function. Good. So that would be the first definition for a continuous function. Okay, and alternatively, we can define the continuous function as follows. So let's say a function f is continuous if, so we can say this if and only if, okay, for any open set, let's say some set T as a subset of Rm, we have this inverse image of Ft that is open. Okay. So you can also see this on the previous picture, right? So here, if we have, let's say we're gonna have, for example, some open set here. Okay, so this is gonna be T. Okay, and correspondingly, we're gonna have this reverse or inverse image. So this is gonna be also an open set, right? But here, there'll be a problem, right? So for example, if we have, let's say, if we have this sort of T from here to here, okay, let's say, okay, to be some open set, okay, but we can see that if we map this backwards to X, then we can see that this maps to here and here, right? So this will be a closed set here, but open here. So this is not open, right? So half closed, half open. That is not either not open or closed, right? So this is not open set. Okay, good. So this will be an alternative definition, right? All right. So yeah, perhaps we should keep it, right? All right, good. So this would be an alternative definition. Okay. So next, okay, we're gonna introduce. So basically what we have here is that we have this definition for the continuous function, right? And this will be alternative definition. So those are sort of equivalent. Okay, we can start from the previous definition and try to prove this this alternative one as some proposition, right? So that's something we can do. And okay, so essentially the proof that'll be pretty straightforward, right? So you can start from the previous definition and try to prove this on those two directions, right? So you can say that if f is continuous, then you can show that for any open set, then this inverse image is open. Or you can also start from this and to try to show that f is continuous from the previous definition, right? On those both of those two definitions. Okay, so we're gonna just skip those proofs, and you can try this if you're interested. Okay, good. So this is a definition for the continuous function. Okay, and remember that we have introduced a very important concept called compact set, right? So if we combine the compact set and continuous function, then we're gonna have another compact set as the result of the function. Okay, so that is called the Weierstrass theorem. Okay. Weierstrass theorem. Okay, so given some in a non-empty compact set Okay, let's call this as some D, which is sort of the domain. Okay, and given a continuous function, some f, which is a map from x to y. Okay, then we have this f. If we map f of this domain to y, so this set that has to be compact. Okay, so this is essentially the Weierstrass theorem. Okay, so again, using the picture that we have in R1, both for x and y. So, for example, we have some function. Okay. Let's say if we have, this would be, for example, from 1 to 2, maybe, okay, and including those boundaries. So this is going to be a closed and bounded set. Okay, and obviously we have this as a closed and bounded set, right, as the value of the function. Or even if maybe you can have some other functions, or maybe something like this, okay, and from 1 to 2, and you could map those, right? This would be the maximum, and so those would be 1 and 2, and this would be the minimum. Okay, again, this has to be still a compact set. Okay, it's closed and bounded. Okay, call this as maybe f2x, fx prime, maybe some gx. Okay, fx, two different functions. Okay, just for two examples. Okay, good. So, but if we have, for example, if we have some holes, okay, if that is not continuous, there'll be a problem, right? For example, if we have, so let's have this inclusive and this is inclusive, and let's say this is fx. Okay, if that's something like this, and even if we take this, let's say take this closed interval from here to here, okay, so we can see that those f of domain, f of d, that's going to be from here to here, but we have to take the union of this, so this would be closed, that's good, but this would be open, right, and closed here, so this would be an open set, so somewhere it's open, so this is not a closed overall, right, so that's going to be a problem, so this is not compact. Okay, good. So, and again, so the proof of this. Okay, so we're gonna skip the proof, and essentially, so we just normally we just need to know what is the sketch or what the idea of the proof, right? So those proofs are pretty long, and it's not very in the episode it's not very it's pretty time consuming, right? So you can always try to work on the proofs by ourselves, and we can simply illustrate the idea of the proof. Okay, so the idea of the proof for this one, for the Weierstrass theorem, is that we simply use the definition, okay, of the compact set of this D, right? So this is our starting point, and we essentially want to show, so for any for all the open cover of that, okay, we can find a finite subcover, right, of this guy, right? So and then we can use those properties that we have from the definition of the compact set, and then and we can use the property of continuous function, and then we go finally go to this, right, to find the finite subcover of f of d, and that completes the proof, right? So that would be essentially the idea of this proof of the Weierstrass theorem. Okay, good. So let's just skip that for now. Okay, so let's move on to something more important, and that would be a sort of corollary of the Weierstrass theorem on R1, okay, on the real numbers. So let's call this as Weierstrass for R. Okay, let's give it a name. So we'll have some domain in X, okay, be a non-empty compact set again. Okay, and here we're gonna have this f. Okay, so it's no longer any random function. We're gonna have this function from X and map to R1. Okay, be a continuous function. So here we can even more specifically say that, so then there exists, okay, some X upper and lower bars in the domain. Okay, so we're gonna have those as our maximum and minimum value for all those image. Okay. And this is true for all the X. Okay. All right, so this is a pretty straightforward corollary from Weierstrass theorem, right? So for illustration on the picture, let's say, for example, we have this, again, some function like this, okay? And if we put our domain from here to here, and this is gonna be the minimum, it's gonna be the maximum, okay? So this is domain. And you can see that this this is gonna be the X upper bar, this is gonna be the X lower bar, and those are inside of this D, okay? And all of those function, those values, they're in between of those two values, okay? So that's essentially this corollary. Okay, so the idea of this proof of this result, okay, is simply by arguing that this we can regard this as the supremum, right, and the infimum, right? So essentially we are saying that the supremum of f of d, or so those are similar arguments, right? Symmetric arguments. So the supremum of the f of d, that cannot be outside of this f of d. Okay, so that's it. That's essentially our key argument here. So the supremum f of d has to be inside of f of d. Okay, so that's essentially what we're saying here, right? So for this part, and also similar for this. So the reason is that we can use some contradiction, right? So we can say that if that is outside of this f of d, if the supremum is outside somewhere, okay, and then we can find some slightly smaller point, okay, that is smaller than that supremum, which becomes closer to this interval, to this f of d, and that point becomes the new supremum, right? And then the supremum, that is no longer the supremum. So that simply becomes the contradiction, right? So that means the supremum that has to be inside of this f of d, and that this part, right? And that also similar for this part, okay? So this would be essentially the idea of the proof. Okay, and we're gonna skip the proof, and now we know how to prove this. Good. So, and lastly, okay, we're gonna have another result from the Weierstrass theorem, Okay, so we're gonna also say something about the argmax. Okay, so let's say so let's have this. So we're gonna have those essentially the same as before. Okay, we just copy and paste those two. Okay, so we're saying that, so if this D is a subset, non-empty subset of X, compact set, and this F is a real valued function, mapped from X to real number, and it's also continuous. Okay, and then we let some Y star. Okay, so that's gonna be the max of Fx. Okay, and we name this D star, okay, as the argmax of Fx. Okay, so that's essentially for all of those X, right? So that'd be the set of all those X which maximize Fx, right? Yeah. So, and then we can argue that we say that this D star is a compact set. Okay. So this is pretty similar to the Weierstrass theorem, right? But that might need some work on this. Okay. So essentially we are trying to show that this D star is compact, right? So so let's first have a little picture on this, okay, and then we can talk about how to prove this. Okay, so this is X, this is Fx, okay. So let's say we have some function, okay, and we have some a interval where we have all of those D stars, okay, which is the maximum of this function. Let's do this again. Okay. Let's suppose that'll be the maximum. Okay. All right. So let's say this is a straight line. Okay. Suppose it to be a straight line. Okay. So this part, that is our D star, right? Okay. So, and let's suppose this our D is somewhere from here to here. Okay, that's pretty wide. Okay, so that our D. Okay, so this is saying that, so this D is a subset of S that is compact, okay, and this F is continuous, and let this Y star to be, so this is gonna be the maximum, and this D star is the argmax, okay. So that's sort of the inverse image of this Y star, and then we want to show that this D star is compact, okay. So essentially, we just prove this by the definition of compactness, okay. And this compactness, that is, we are using the compactness of the that is also both closed and bounded, right? And so for the boundedness, this is pretty straightforward, right? So that is simply bounded by the D, okay. And for the closeness, that needs a bit of more work, but that's essentially, we can try to argue that the complement, okay, of the star, that is open, okay, and from that point we can show that this star is closed, Okay, and then together we can show that this D star is compact. Okay, so this proof might be a bit longer. Okay, then you can work on this if you're also interested in this. Okay, all right. So then that'll be almost everything for this episode. So we gave some definitions on let's see, on the functions, right? And then we introduced the continuous functions. So where we have two equivalent definitions for continuous function, and you can try to prove from the first one to the second one. And we showed the Weierstrass theorem, where we can argue that given some continuous function and we can map from some compact set of domain to some image that is compact. Okay, and then we can apply this Weierstrass theorem to some corollaries on some real numbers, and we can find those maximum and minimum all of those functions and those axes there inside of the domain. Okay, and we can also show that this the last result here, right? If we have this, again, we have some non-empty compact set and some continuous function, and we can show that for the last result here, right? So we can show that this for some maximum value of this function given some domain, then the inverse image of that y star, then we can show that this D star is also compact. Okay, so that'll be everything for this episode, and hope this will be useful. Okay, good.